Hi everyone, welcome to the third video in the video series I have for the package tsBNgen. In this video, I'm going to continue where I left off in the second video that I talk about this package. I walk you through these examples and I tell you, for example, what each this variable represents, how you can use this tsBNgen. Today, I'm going to walk you through this code in Python now. So I'm right now in the Jupyter Notebook. How can you access this Jupyter Notebook? So this Jupyter Notebook, you should go to my GitHub. If you go to my GitHub right now, I'm not logged in. So you go into code and you type git clone and you get a clone. So that's one way to do that. This is a recommended way. If you do not want that, if you want to actually follow the examples, so that's one way, because this example time series generation example is here, right here. So you can actually get a feel about this package. Now, also alternatively, if you want to use your own Jupyter Notebook and you don't want to go through this example, you can also go ahead and install this package. Where is that? Using pip install tsBNgen, right? You might receive a warning. I don't know. In last year that I import this one to the Python library, there was no warning. You might receive a warning, but still the package is going to work great. Now, after you install the package, so a couple of things for people that are not really familiar. So I assume that you know Python and Anaconda distribution very well. You know how to install the packages in Python, how to create the virtual environment in Anaconda. But if you don't know that, it's no worries. So what you can do, you can actually go ahead and install Anaconda first and install Python as well. Python 3.9 at the time of recording this video is the latest release of the Python. Then you go to Anaconda prompt. You go here and click Anaconda prompt here. All right. So once you go to Anaconda prompt, what you want to do is more advanced and more professional to create a virtual environment. You use this command, conda create -- name. tsBNgen practice is the name of my virtual environment. Yours can be anything you like. And then Python 3.9. I would like to install Python 3.9. So you actually want to install the latest version. So depends on when you see this video. This Python 3.9 can be different distribution. So you're gonna go over installing some parameters, some packages. Python 3.9-9-6 is installed. Pip is you install the package. A SQLite, for example, is a database, the file in your computer. After that, you want to activate the environment, virtual environment, with the conda activate tsBNgen practice. And when you activate that, this base is going to be changed to tsBNgen practice. Then you're gonna go and install NumPy that we need here and pandas. And then after that, you install NumPy and pandas, you can install tsBNgen if you would like. So might get a warning, but still it's going to be successfully installed. Then what you need to do, install a Jupyter Notebook to follow this example. Jupyter Notebook is really great for tutorial. And when you actually create a package, you want to show it to the world as have some examples. Jupyter Notebook is a great tool to have. Otherwise, this package I wrote in the VS Code, actually Visual Studio Code, which is freely available as well. Now, so to install a Jupyter Notebook, I would there are a lot of commands in the internet. What I would recommend is that you follow this one. You type conda install -c conda forge notebook. This install all the necessary packages you want for Jupyter Notebook. Okay. Then once you go over this, install them, what you want to do, install conda install -c conda forge nb notebook conda kernel. This install the necessary kernel for your Jupyter Notebook, and then you're good to go. Then just go to the your Anaconda prompt and type Jupyter Notebook. So this will launch the Jupyter Notebook, and you can go to the folder that you clone this Jupyter Notebook file. All right. Now that we are here, we are actually kind of ready to go over the example together. So what you want to do is first start here. We're gonna run this. All right, successfully we can run this one. and import all the necessary files. I walk you through this example in the last video. If you haven't watched this, I will put a link in the description, and then go ahead and watch this one. I give you an idea what each parameter or variables represent, but I can tell you more a little bit here. So T is the length of through time, the number of time points you have per time series. N is the number of observations or samples you have. So number of level 2 means the binary, 4 means that this number of level is the number of levels for a variable, for a discrete variable, multinomial variables. Math is the adjacency matrix. Node type, whether it's a discrete and continuous. This is related to the first video that I have, that how you can represent the conditional probability distribution if you have a discrete or if you have a continuous variables. And then CPD, the actual conditional probability distribution, the parent for each node. So we follow the topological ordering of the graph. The first node is root node is a 0, then is 1, and then is 2. So what is the parent of root node 0 at the first time point, at the initial time point? Because I explained in the last video that parent is in the first time point. And then parent 2 is going to be the time T2 onward. All right. So then that's going to be no parent. Node 1 is going to be it's going to have 0 as a parent, and node 2 is going to have 0 and 1. All right. And then you loop back, it shows the interconnection through time, the temporal interconnection. So loop back 1, 0, 0 means that the node 0 at time t plus 1 is connected to the node 0 at time t, and what's the loop back is actually equal to 1, means that at time t minus 1 is connected to t, and it's connected to t plus 1. All right. And loop back for the node 1 at time 1 is connected to the time t minus 1 is connected to time t, and because the loop back is actually equal to 1. So in the last video I discussed all this. All right, so you go ahead and instantiate this. You see that parent is defined twice. Ignore this one, you can also remove it, but they are both the same and it doesn't create any problem for your code. So you instantiate the object using this tsBNgen is the name of the package, and this is what I pass in the init. All right, then you come here and you run this function. So I remember I explained to you in the last video that you need to worry about these two only. This is if you want to run a classical dynamic Bayesian network, what you see in the literature. The node at the time t minus 1 is connected to the node at the time t, right? This one, if you want to do any advanced stuff. The last video I explained about this. So you go ahead and generate your time series. All right, this function will take care of this for you. And so now let's run this package. Actually, see what it gives us. So I already run this one and run it. But then this one, if you run this one, should be not really, it's gonna be really quick. Now, so here, so once you get the time series here, now you want to access this element of the time series, right? So we have node 0, we have node 1, and then we have node 2. Right, we have 3 nodes here. Node 0 is a root, and then the topological order that I explained about this example in the last video. So now we have 2,000 samples for each node. For each node, we have 2,000 samples, right? So because we have 2,000, let's say, students, so each one has this characteristic, each one has this, I don't know, variable A, B, and C. So the way to access it is using this method, BN nodes. Right, 0 means that the first variable, second and third, and then 0 is 1 means the second sample. Indexing starts from the 0 at Python. All right, so if you run this one, all right, great. So now let's take a look at that. This is the first variable, which was binary. You have 1, 2, 2, 1, 2, 2, right? And this is the second variable, discrete variable that was has 4 levels, right? Remember, this has 4 levels. So 2, 2, 4, 3. And this was actually the continuous distribution that we have. So this actually generates the data for you for this distribution so easy. You can choose this T to be 1,000. You can choose this N to be 1,000,000, right? And it generates a distribution for you. Okay, great. Now you can go to architecture 2. And do the same thing for architecture 2. But in the video, I talked about the last architecture, which was this is HMM. This is the architecture of the HMM, actually. Now, so for the architecture of the HMM, which is very important, there are many ways. HMM, you know, is a generative model. You can actually generate new data actually from HMM. But this allows you actually to simulate HMM very easily. Some people are maybe having difficulty to generate the HMM type data. This actually gives you to generate based on your own distribution. All right, so let me walk you through this one. Now, T is 20, again, 20 points in time. I'm gonna change this one, actually. I'm gonna change to 50. And then N is 1000. So this is import time that you have here to see how long does it take for this code to run. This eventually we're gonna run this command to see from the finish to start to finish, how long does it take. Now, number of level is 4. Why is that 4? Why do we have only 1? Because I chose that a state takes 4 values, 4 different values, and the observation for me is continuous. So this number of level, remember, only denotes the number of discrete, the number of levels for discrete nodes, right? And then adjacency matrix is the adjacency matrix of the HMM, and the node type is DNC, as I told you. The first one is discrete, correspond to this, and the continuous. And the CPD. At the initial point, all the conditional, all the states are equal likely. And this is a distribution of the continuous nodes, right? So we should have 4, right? We should have 4 for any possible any possibility of the parents. We start from mu0 all the way to mu3. We have 3. We have 4 possibilities. The parent of node 0 at initial time is nothing, is a root node, and the parent of node 1 is node 0. And the same thing you can do for CPD2, and the loopback also is loopbacks is 1 for 0, 0. Because observations at HMM are not connected. So node 1 is not connected to any, the observation is not connected to a state or the observation at time t+1. All right. And the states are only connected to each other. Okay, great. So let's just go ahead and run this one. We go ahead and run it. All right, 3 seconds it takes. And now you can access this one. That's it. So 50. This is 50. You can go ahead and play with this one. Choose anything you like. Let's go on 5, right? Less than 1 second. And that's it, right? So if you look at that also, it makes sense. If you are here, so this is if the parent node, if the state is 4, right? If the state is 4, you're gonna pick a sample from this distribution with the mean 80 and the sigma standard deviation 5. So it makes sense that you get 73, right? When this is 3, right? Based on some transition matrix that you get, this is 3, then you go to this CPD2, right? If this is 3, you get 65. That's it. Does it make sense? Absolutely. With the mean 60 and the standard deviation 5. So you can actually follow this stuff. And they say, for example, for the next 4, actually you get 81. All right. So you see the package is doing something completely meaningful and is actually working as expected. If you like this video, please subscribe to the channel, like and share it with your friend, and ask me any question you have under the video. I try to help you. I have more packages to share, more videos to go over that, and very excited to post more in YouTube. All right, thank you so much.